So consider the linear functions of the form g1, g2 up to g sub n. So you have n linear functions in the dependent variable x1, x2 up to xn. Right. So in this case, the dependent variable is x1, x2, and xn, and the independent variable
is going to be t.
You have the first order system of linear equations of this form, dx1 dt equal to a11 of t x1 plus a12 t x2, and you do this up to a1n of t times xn. This is just one differential equations. The second differential equation is dx2 dt equal to a21 t x1 plus a22t x2. We do this up to a2n of t xn. Right. So the coefficients in this case, a11, a12, so on and so forth, can be constant, but can be some function depends on the independent variable. Right. And you have n differential equations. Right. So you have a and 1 of t times x1 plus a and 2 of t times x2 plus a and n of t times xn. So you have again n different first order differential equations. Okay. Now with this system, I'm going to call this the homogeneous system. Okay. To distinguish with the non-homogeneous system, when you introduce an extra force term or the external force into the system, right, that means for each differential equation, if you introduce some external force, let's say F1t plus F2t plus Fnt, then this system is called the non-homogeneous system. Okay, we're going to revisit this homogeneous and non-homogeneous system later on in the lecture. But for now, this system is the general form or the normal form of the first order system of linear equations. Okay, and I'm going to name this system system 1 so that I can use system 1 later. Right. And system 1 is called the first order linear system. So system 1 is called the first order linear system. The value in front of the dependent variable, right, the coefficients a11, a12, a1n, are continuous function or can be constant, depends on the situations. But anytime you consider the system of first order linear differential equations, the coefficient has to be the continuous functions, as well as the functions f1, f2, up to fn. Right. So in general, the coefficients aij and fi are continuous functions on the common interval, some interval capital I. Right. So the index I is going to go from 1 to n, and the index j is also going from 1 to n. Right. When the function f sub I equal to 0, again, for I is going from 1 to n, again, I is the index. So when f sub I equal to 0, the system 1 is said to be homogeneous. Is said to be homogeneous. Otherwise, it is non homogeneous. That means if f sub I is a constant or some function, then you say the system is non homogeneous. If again f sub I equals to 0, then the whole system is called the homogeneous system. All right. So as you can see, it's a little bit troublesome to write every single differential equation in the system out explicitly, right? So it's take a lot of time and effort in doing the writing. So what we do is that we're going to turn the system into matrix vector form. Okay. So now I'm going to do the matrix form of a linear system. So if capital X, right, so with the arrow on top indicates a vector, capital A of t without the arrow on top indicate that's going to be a matrix. Right? And capital F of t with the arrow on top is again a vector, so it denotes the respective matrices. Right. So the naming. Right? So I say that the capital letter with the arrow on top indicate vectors. Right? It's still the vector, but you can call it a matrix. It doesn't matter. But to distinguish between the matrix, the coefficient matrix that we're going to see, and the vector solution or the solution vector, then that hence the notations that I use here. Right. So vector, it has either the column vector or the row vector. when you have the capital letter without any arrow on top, that's my indication for a matrix. Okay. So instead of writing dx1, dx2, and so on and so forth, I'm going to put everything together into a vector. Instead of all of the coefficients multiplied with a dependent variable, I'm going to put those coefficients into a matrix. It's called a coefficient matrix. Okay. So for dependent variable, I have x1t, x2t, up to xnt. Right. It's just a collection of all the dependent variables. For a of t, I got A11, A12 up to A1n, then A21, A22 up to A2n, and then I have AN1, AN2 up to ANN. So this is the n by n matrix. Again, the matrix is just a collection of numbers, and you put those numbers in rows and columns. And because these entries are collected from the coefficients of the dependent variable, so we call this matrix a coefficient matrix. Now for F, right, the external force, it's going to be F1t, F2t, up to Fnt. So using these notations, we can write down the system of linear first order differential equation as follow. Then the system of linear first order differential equations can be expressed as so here x1 prime of t to x2 prime of t down to xn prime of t equal to the coefficient matrix A11, A12 up to A1n, A21, A22 up to A2n, and then A1n, AN1, AN2 up to ANN. Multiply with x1t, x2t, down to xnt, plus the external force F1t, F2t, Fnt. Okay, and to make the writing even shorter, we're going to write this as capital X prime equal to A times capital X plus capital F. Right. So again, capital A is the coefficient matrix, capital F is the external force of the forcing term. And this, if capital F is different from 0, then this system is a non-homogeneous system. If capital F is equal to 0, then you have a homogeneous system. We're going to move on to example 1. So in this example, the idea is just to rewrite the system of differential equation in terms of the matrix in vector form. Okay. Now look at the first matrix, the first system right here. This is the homogeneous system because you don't have an extra forcing term. It's just the dependent variable x and y, right? And the independent variable in this case is little t. Okay. So in terms of matrix vector form, if capital X is equal to xy, then the matrix form of the homogeneous system is, right, so the left-hand side is indicating the derivative, right, differentiation. You have x prime, y prime, equal to now the coefficient matrix multiplied with the dependent variable. Right, for the coefficient matrix, you just take all the number right in front of x and y. So I have 3, 4, 5, -7 times x and y. If you perform the matrix product between these two matrices, you, of course, will get back 3x plus 4y and 5x minus 7y. Or you can write, this is capital X prime equal to 3, 4, 5, -7 times capital X. Now I'm going to move on to problem B. So in this problem, you have a system of 3 linear differential equations, right? And this system is actually a non-homogeneous system. So can you, this is the non-homogeneous system. Okay, because when you look at the system, you will see that on the right-hand side, not only you have x, y, and z, which are dependent variables, you also have a plus t on the first equation, plus 10t in the second equation, and the plus 16 in the third equations, right? So those are the forcing term or the external force applied to the system, okay? And therefore, the system is non-homogeneous. And we're going to rewrite the system into a matrix vector form. So this is going to be x prime, y prime, z prime equal to the coefficient matrix 6, 1, 1, 8, 7, negative 1, 2, 9, negative 1 times x, y, z. Okay. Now remember, but this system is the non-homogeneous system, so you have an extra vector for the forcing term plus t, 10t, 6t. So the next concept is called the solution vector, right? So remember what we have done so far is that we try to find the solution of differential equations. So we get the general solutions, we get the particular solution, but for general solution, like we have one solution, one general solution, or we have one homogeneous solution, or we have one particular solutions. But in this case, because you have system of differential equations, you need to have multiple solutions at once, right? And you put all of the solution into a vector. It's called the solution vector. Okay. So a solution vector on an interval I is any column matrix of the form x1t, x2t up to xnt, whose entries are differentiable functions satisfying the system x prime equal to ax plus f on the interval I. When you get the solution of one differential equations, right, it's sometimes very simple just to plot the solution and visualize the solution. But when you get to the system of differential equation, it's not that simple to actually solve the solutions analytically, right? Because there's too many, there are too many variables moving, right? So all of the solutions in the solution vector can be viewed as something called space curve, and we can analyze that geometrically or graphically. Okay, all right. So a solution vector of n entries is equivalent to n scalar equations. So for instance, you have x1 equal to some function phi sub 1 of t, x2 equal to phi sub 2 of t, so on and so forth until you get to the last solution, x sub n equal to phi sub n of t. N can be interpreted geometrically as a set of parametric equations of a space curve. So the second remark is related to what we're going to do is in the case when you have two solutions, right, in the system of two linear first order differential equations. So in the case of n equal to 2, the equations x1 equal to phi 1t and x2 equal to phi 2t represent a curve in the x1 y1 plane. Sorry, x1 x2 plane. And the curve in this plane is called trajectory. So curve in the x1 x2 plane is called trajectory. And the x1 x2 plane that we're going to deal with is called the phase plane. And we're going to go back and take a look at these two concepts, trajectory and phase plane, sometime very soon, probably tomorrow or at the beginning of next week. Okay. At this point, I just want to introduce to you the solution back then. And again, most of the time, we're not going to be able to look at the solutions. You could be able to solve the solution analytically. So most of the time, what we do is we look at the solution geometrically or graphically. All right. So I'm going to move on to example 2. So in this example, I want to verify that the two solutions given here is in fact the solutions to the differential equation or the system differential equation, capital X prime equal to 1353 capital X, capital X. All right. So before doing that, I'm going to rewrite x1. Right? So you have, there's the coefficient multiplied with the function e to the negative 2t. And for x2, you have the coefficient vector 3, 5 multiplied with the function e to the 6t. I'm going to rewrite this as e to the negative 2t, negative e to the negative 2t. It's convenient for us to check that is these solutions are in fact the solutions to the given system. Okay, so x2 is 3 times e to the 60. This is 5 times e to the 60. So to see if the solutions satisfy the system, what you do is you want to prove or you want to show that the left-hand side of the system equal to the right-hand side of the system. So that is, you take the derivative of x1 and substitute it in here on the left-hand side of the system. And hopefully it's equal to the matrix product, the coefficient matrix multiplied with x1. Okay, so I'm going to start with the derivative, right? So x1 prime is equal to, so the derivative of e to the negative 2t is minus 2 e to the negative 2t. And negative e to the negative 2t, the derivative of that is 2 times e to the negative 2t. And for x2 prime, you have 18 e to the 60 and 30 e to the 60. Okay. Then we see that, right, so you do a times x1, given a, again, it's the coefficient matrix, 1, 3, 5, 3, multiply with x1, that is e to the negative 2t, negative e to the negative 2t. Right, so x1 is right here. Now, next, I'm going to perform the matrix product. So I have 1 times e to the negative 2t plus 3 times negative e to the negative 2t. I got e to the negative 2t minus 3 times e to the negative 2t. Then for the second entry, you have 5 times e to the negative 2t plus 3 times negative e to the negative 2t. That is negative 3. Okay. So for each entry, simplifying, you get negative 2 times e to the negative 2t and positive 2 e to the negative 2t, which is equal to x1 prime that we found over here. Okay, so now for the second solution, have a times x2 equal to 1, 3, 5, 3 times x2, which is 3 times e to the 60 times 5 e to the 60. Again, you're going to perform the matrix product, matrix multiplications, and you get 3 e to the 60 plus 15 e to the 60, and then 15 e to the 60 plus 15 e to the 60 again. This gives me 18 e to the 60 plus 30 e to the 60, and this is equal to x2 prime. Right? And that's how you perform or how you check if the solution, right, solution vector satisfy the system of differential equation. Now I'm going to move on to identify the initial value problem. You have heard about this already many times throughout the course. For initial value problem, that means you need to have a differential equation and you need initial conditions. So for the initial value problem, let T0 denote a point on the interval. All right, so let T sub 0 denote a point on the interval, on an interval I. And this T sub 0 is called the initial point. And you have capital X sub 0 is equal to x1 t0, x2 t0, up to xn t0. Then we have the initial value problem that solve the differential system of differential equation x prime equal to a times x plus f of t, subject to x of t sub 0 equal to x0. Right? So again, initial value problem is the same idea. You need a differential equation, you need a set of different of initial conditions, right? So in this case, you have multiple differential equations in the system. So not only you need to have a system of differential equations, but you need to have a list or a vector of initial conditions, right? That match for each differential equation. So that's how you set up the initial value problem, right? You can always solve for the differential equation or the system of differential equations to obtain the general solution, but you need the initial conditions to obtain the particular solution. So next, the existence of a unique solution. So let the entries of the matrices A and F be functions continuous on common interval. Right? Let's just assume you have an interval I, and the functions in the coefficient matrix in the fourth term are continuous function on this interval. That contain the point t sub 0. That means you need to have the initial point, initial conditions. Then there exists a unique solution to the initial value problem on that particular interval. So this statement or this theorem, just to say that, okay, when you find the solution to the initial value problem, the solution exists and the solution you found is unique. Okay, so there's nothing crazy there. All right, now the superposition principle. That again, you have seen this one already, right? When you have, let's say, that's just one differential equation, and you get the solution, right? So let's say y1 and y2, a linear combination of y1 and y2 is also a solution, right? It's similar to that for the superposition of a system of linear first order differential equation. You have a solution, right? A solution set of the solution vectors, and the linear combination of the solution vector is also a solution to the system. So you say let x1, x2, up to xn be a set of solutions vector of the homogeneous system on an interval I. Then the linear combinations, you have x equal to c1 x1 plus c2 x2 up to cn plus xn is also a solution on the interval. Okay. So again, I want to note here the c1, c2 up to cn are just some arbitrary constants. So here, quick notes. The ci's with arbitrary constant for I going from 1 to n. Consider the following solutions. That you have x1 equal to cosine of t minus 1/2 cosine of t plus 1/2 cosine of t. And then the last entry is negative cosine of t minus sine of t. And x2 equal to 0 e to the t 0. So these two solutions are the solution of the system. X prime equal to 1, 0, 0, 1, 1, 0, and negative 2, 0, 1. So this the coefficient matrix. So this is negative 1. Multiply with the variable vector. So by the superposition principle, the linear combinations x equal to c1 x1 plus c2 x2 is also a solution to the system. And you could be able to do that to form a linear combination of solutions when the solutions are linearly independent from one another. Right? If the solutions are linearly dependent, then you cannot do that. And of course, you can check if the two solution vectors are linearly independent or linearly independent or not. What you do is you calculate the Wronskian between the two solutions. Right? And at this point, you know how to do Wronskian. However, it's not quite the same formula as you do for the Wronskian in just one differential equations. The Wronskian, we'll see later, the formula is a little bit different. It's easier to calculate. Okay, so before the Wronskian, we want to recapture the concept of linear dependence and linear independence. Okay. Now again, suppose you have a set of solutions vector, x1, x2, up to xn, of the homogeneous system, not the non-homogeneous, but the homogeneous system. And we say that the set it is linearly dependent on the interval considerations if there exists constant C1, C2 up to Cn, not all 0, such that x equal to C1 x1 plus C2 x2 to Cn xn. Right? Again, this is just the linear combinations that we see earlier. Right? So this is right the if the set of vector is not linearly dependent on the interval, it is said to be linearly independent. Okay. So the remark on this is that I'm going to talk about the case of two solutions vector. So if you two solutions vector, x1 and x2, are linearly dependent. If one is a constant multiple of the other. In the case of n greater than 2, a set of solution vector is linearly dependent if we can express at least one solution vector as linear combinations of the remaining vectors. Again, moving on to the next concept by Wronskian. We're going to use Wronskian or calculate Wronskian to determine if the solution vectors are linearly dependent or linearly independent or not. Because again, we want to know if you can write the solutions as a linear combination, so that you have another set or another solution that satisfy the differential equation and satisfy the system of differential equations. So the Wronskian, right? So the concept of Wronskian determinant is a test for linear independence. The concept of Wronskian determinant is a test for linear independence. Okay, so let's consider the following solution vector. Okay. So let x1 equal to x11, x1, x21 to xn1. x2 is equal to x12, x22 to xn2. And the last solution vector is x1n, x2n up to xnn. The n solution vector of the homogeneous system, again, the homogeneous system is of the form x prime equal to ax, right, without the external force F. On an interval I, then the set of solution vectors is linearly independent on I if and only if the Wronskian of x1, x2 up to xn are different from 0 for all value of t in the interval I. Now, the question is, how do you perform the Wronskian determinant calculation? Right? Unlike the Wronskian that we learned before, right, where you have the solution and you take the derivative of the solution, y1, y prime, y2 prime, the Wronskian for the system, or to determine if the set of solution vectors are linearly independent or not, you just basically form the determinant of column vectors. Right? So this is the determinant. You start with x1 vector column, and then x2, and then up to xn. So the Wronskian can be calculated as x11, x21 up to xn1. Right, so that's the capital X1. Then you have x12, x22, xn2. So on and so forth up to x1n, x2n, x and n. This has to be different from 0 for all the value of t in the interval I. So let's tackle one last example. Again, you have seen this example earlier when you have two solutions, x1 and x2, and we see that these two solutions satisfy the system of differential equation. We did that already. But we don't know the fact that these two solutions vectors are linearly independent or not, so we need to do that calculation. So again, from this, we're going to rewrite the vectors as e to the negative 2t and negative e to the negative 2t. The second vector is 3 times e to the 60 and 5 times e to the 60. Now, again, to check if the solution vectors are linearly independent or not, we perform the Wronskian of x1 and x2. So we just basically form the determinants of column vectors or column matrices. Right? So e to the negative 2t, this is negative e to the negative 2t, then 3 times e to the 60, and this is 5 times e to the 60. And again, this is the 2 by 2 determinant, straightforward calculation. You get 5 times e to the negative 2t times e to the 60 plus 3 times e to the negative 2t times e to the 60. Or this is 5 e to the 4t plus 3 e to the 4t, or this is 8 times e to the 4t, which is different from 0 for all the value of t. Right? Because of this result, we conclude that x1 and x2 are linearly independent. Again, when you talk about Wronskian, not only you can check that x1 and x2 form are linearly independent if Wronskian is different from 0, but also you can say that x1 and x2 form a fundamental set of solutions. Right? So that's the key to the Wronskian. Right? So that's the next definition is the fundamental set of solutions. Then assume that you have n solution vectors and they are linearly independent due to calculation of the Wronskian. Be different from 0. Right? And from that result, we can also conclude that the set form of fundamental, or the solution vectors form a fundamental set of solution, or basically the basis of the solution to the homogeneous system.